All right. Well, thanks for the invitation, Abby. So I'll tell you about some work that I did mostly during my postdoc at the University of Washington. This is joint with James Sanderson, who's now at Monash University, Mohit Singh, who's now at Georgia Tech, and Rekha Thomas, who's still at the University of Washington. And we were all in Seattle at that point. So I'm going to start with like some very basic stuff. So please, tell me to speed up if you get bored, and slow down if I think that you know things that you don't know. So just in case you get bored, here is what the point of the talk is. So I want to certify the non-negativity of a symmetric polynomial over the hypercube. So this relates to a very old problem, which is just to certify the non-negativity of a polynomial, right? This is central in real algebraic geometry. And well, normally, we have this technique of sums of squares, which we can use there. And the runtime is, if you have an ideal, which we'll see how it all works during the background, the runtime is usually the number of variables to the order of the degree that you have. And so, well, for many problems, that means that, well, if you have a lot of variables, this will not be good enough, even if the degree that you need is very small. And so what we want to do is that we want to look at a specific setting where you have a symmetric polynomial and you're over the hypercube, and we want to show that there the runtime does not depend on the number of variables. So you can have a very large number of variables, or the number of variables can go to infinity, and you'll still be able to say something. So I'll try to make clear why our setting is interesting. Does this really ever happen that you have a symmetric polynomial over the hypercube? And you do, so I'll give some examples of that. And then I'll tell you a little bit more about our results. And then if there's time, I'll tell you how this relates to the theory of flag algebras from Sasha Hasbahov. And if there's time, I'll tell you a little bit the future directions that we're going into these days. OK, so let me tell you some very basic things about sums of squares. So I said that a polynomial is non-negative if whenever I evaluate it on any point of Rn, then I get at least 0. And so a very, very simple idea is to say, well, if I want to show that a polynomial is non-negative, I could just write it as a sum of squares, right? A square of a polynomial is non-negative, a sum of squares is non-negative. So if I can write it as a sum of squares, then I'll have a nice certificate of the non-negativity of my polynomial. The problem is that we've known for quite a while now that not all non-negative polynomials are sums of squares, right? So in 1888, Hilbert showed that not all non-negative polynomials are sums of squares. The history there is a little bit muddy. In 1885, a 23-year-old Hilbert, who looked younger than that, presumably, went to the PhD defense of a 21-year-old Minkowski. And during the defense, Minkowski was asked, are all non-negative polynomials sums of squares? And he answered no. And it's unclear, did he give a full argument? I mean, he passed his defense, but we don't really know how much of an argument he gave. But what is sure is that 3 years later, Hilbert published a paper showing that. He did show more. He did exactly characterize which non-negative polynomials are always sums of squares, like univariate polynomials, for example. But his proof was not constructive, and it took actually quite a while to have a first example of a non-negative polynomial that is not a sum of squares. So we usually credit this example to Motzkin, but really he had come up with the polynomial for something completely different, and it's Olga Toskitad who, when she saw this polynomial used at some seminar, who realized that it was not a sum of squares and that it was non-negative.
Who is this?
Olga Toskitad. Yeah. So, yeah, I think we should probably credit it to her. So that was, now we know many more non-negative polynomials that is not a sum of squares. OK, so.
Why did it take so long to find such a simple polynomial?
I know. I don't know. I mean, to be fair, though, I think that the theory of sums of squares kind of has become more and more popular as time passed, right, as optimization rose. So it might just have been that people were not all that interested in it.
It's even simpler. There is a homogeneous version.
True.
Z variable, and then it's almost the first one you'll think about.
All right. So how do you find a sum of squares certificate, right? So not all non-negative polynomials are sums of squares, but some of them are. So how would you find your certificate? Well, you have some polynomial of degree 2D. All right. So you'll take a vector of monomials of degree at most d in your polynomial ring. I mean, any basis of the elements of degree n most d of your polynomial ring would work, but this is a very nice and natural basis to take. And so then your polynomial is a sum of squares if and only if there exists some positive semi-definite matrix Q such that P is equal to your vector of monomials transpose Q times your vector of monomials. And the reason this works is that, well, one of the definitions of a positive semi-definite matrix is that it can be written as BB transposed. So I really get my vector of monomials transpose times B dotted with the same vector again, right? So then I'll square each component and add them up, and that's how I'm going to get my squares, right? So if I had this polynomial here, I look at it. I mean, if you're very visual, maybe you can kind of imagine that it's non-negative. But if I write it in this way, then it's very clear, right? I have 1, which is a square, plus another square, plus another square. This is clearly non-negative. And so to go from there to there, well, this is a polynomial of degree 2, so I'll need to take all monomials of degree at most 1, so degree 0 and degree 1 in variables x1, x2, and find this PSD matrix here. And the reason that I get my squares is because I have this nice decomposition into B transposed. And so really I can just think like, oh, I'm taking this vector times this column gives me x1 over 2 plus x2 over 2. And I get the same thing here from the last row with this column vector. And so then together I get this square. So, good. But we said not all non-negative polynomials are sums of squares. So there's many times where your polynomial is non-negative where this won't work, right, to give you a certificate of non-negativity. And so Hilbert was disappointed. And when you're important and you're disappointed, you yell it to the world. So he said, here's my problem. Are all non-negative polynomials sums of squares of rational functions? I'm really disappointed that they're not sums of squares of polynomials. So are these sums of squares of rational functions? And that was his 17th problem, which was solved by Artin in 1923. And he proved that, yeah, actually, every non-negative polynomial can be written as a sum of squares of rational functions. We don't have an algorithm for that. But so this kind of gave the idea for people, well, not an effective one. Well, can we do something similar for if I'm trying to certify non-negativity over maybe some algebraic sets or varieties and have some efficient algorithms there? And so that brings us to the idea of a sum of squares modular ideal. So let's say that I want to certify that a polynomial is non-negative, but not everywhere, just over the solutions of a system of polynomial equations. And so your polynomial equations can really represent anything, right? You can use that to model really tons of things. So one thing I could do, for example, is I could want to show that 1 minus y is non-negative whenever x squared plus y squared is equal to 1. So I really want to show that y is at most 1 whenever I'm on the unit circle. I draw the picture, and yes, every point of my unit circle actually has a y component that is at most 1. Great. How could I prove it more algebraically? So I could try to write 1 minus y as a sum of squares, but I shouldn't succeed, right? Because 1 minus y is not greater or equal to 0 everywhere. So I write it partially, but then I'm off a little bit. But what I'm off by, proving, oh, it's something that I know is 0 for every point that I care about. X squared plus y squared minus 1, that is always 0 on my unit circle. So I have something that is non-negative everywhere minus something that is 0 on every point that I care about. And so the part that's the sum of squares I can rewrite using my PSD matrix, but that's really the general idea is I want to write a sum of squares plus or minus something that I know is 0. So in general, I will have an ideal that is generated by a set of polynomials. So here, just generated by the polynomial x squared plus y squared minus 1. And then I have its real variety, which is just a set of roots of all these polynomials. So here it's my unit circle. And so I'll say that a polynomial is a sum of squares modulo my ideal if I can write p as a sum of squares plus something that I know is 0 on every point that I care about. So plus some h that lies within my ideal. And so then if I can do that, then I have certified non-negativity for every point that I care about, for every point in my real variety. So if it so happens that every polynomial that I'm squaring has degree at most d, then I'll say that this is a d sum of squares, modulo my ideal. And so this d, this degree, really represents the hardness of the problem. So if d is small, then it's going to be a nice tractable problem. If D depends on the number of variable, then this is probably a very, very hard problem. So the way that I'm going to find a certificate is I'm going to find some positive semi-definite matrix Q such that P is equal to V transpose QV modulo my ideal, where V is a vector, not just, so it's going to be a vector of my basis of the elements of degree at most D of my quotient ring. So before I had all the elements of all the monomials of degree at most D, and so here that's overkill because I have my ideal, so I can take something smaller. But certainly D will tell you how long this vector is and how big this matrix Q is. So the bigger degree that you have to use, then the longer it will take to solve. And so this is n to the order of the degree. So that means that if your degree is a constant, then you can do this in polynomial time. If D is not a constant, then you're screwed, right?
This is assuming you can do semi-definite programming, assuming you have an explicit representation of the ideal. I mean, reducing the number of coefficients.
That is very true. So that's actually a point that I should make, is that, so before we said not all non-negative polynomials are sums of squares. Here, if you have a system of polynomial equations, modulo a few very simple assumptions, actually, you know that you will be able to do this. So D might be big. So D might actually depend on n. But for most problems that we can think about, that we care about, D will be at most n, the number of variables. And then you'll be able to do it. So except if you're going in a pretty, weird direction, if you have just a problem that you're actually trying to solve, if you're really modeling something pretty realistic, you should be fine.
Right, you're talking about the hypercube.
Oh yeah, for the hypercube there's no problem.
Example, right? In the hypercube x squared equals x.
Yeah.
And so all polynomials are multilinear, so
yeah.
you never get degree.
Yeah. For hypercube it's never a problem. For a hypercube you will always be able to do it with D at most n.
But D equals n is still quite large.
Yeah, exactly. That's still terrible.
These guys in real algebraic geometry work with some degrees can be 2 to the n or larger.
Yeah, but over the hypercube for sure you will not run into that problem. But still, even if D is a constant, polynomial time is not that great, right? If n is big, polynomial time is terrible. If you're doing this for some combinatorial problem where the number of variables goes to infinity, this is terrible. And so this is kind of the point of the talk, is how can we make this better? How can we make this runtime only depend on D whenever you have symmetry and you're over the hypercube? Okay, so this is our setting. We have the K-subset discrete hypercube. And so by that I mean the hypercube whose coordinates are indexed by K-element subsets of a ground set of elements 1 through n. So for example, you could have a graph on n vertices, and so your ground set of elements would be your vertices. And your edges would actually be what you're manipulating. So your edges would be 2-element subsets of your vertices. Or maybe you have a K-uniform hypergraph. Then you would have K-element subsets of your vertices. And so I want to minimize a symmetric polynomial, or maximize, it doesn't matter, over my K-subset discrete hypercube. And so by symmetric here, I mean that it is invariant under the symmetric group of order n. So really my symmetric group is acting on my ground set of elements. Right? So it's acting on my vertices, but I'm really looking at the induced action on my edges, for example, so on my K-element subsets. So an action S being applied to the variable x of I1 through Ik gives me x of S applied to I1 through S applied to Ik. Right? So I'm really looking at the induced action. So how do I want to do that? Well, I want to do it in a clever way, right? I want to, optimization and certifying non-negativity are really two sides of the same medal. We're going to see it in a few seconds. But so I want to do this by finding a sum of square certificates over my K-subset discrete hypercube in a way that it exploits symmetry. I want to find a runtime that is independent of the number of variables.
When you say independent of n, you don't mean totally independent of n.
So it's going to depend on D, which can depend on n.
Okay.
But it's only depending on D.
It will just depend on D, which can depend on n.
Call it parameterized complexity.
maybe I'm missing something, but don't you have to write down the solution, which already is going to...
To find the optimum, you don't have to, I mean, just the value of the optimum.
I see.
So I'm going to show you how to do it,
Okay.
right? So that's kind of the point of the talk.
What is the dependence on D, just out of curiosity?
Oh, it's bad. I mean, it's
Yeah.
exponential indeed,
Exponential.
but it's not a tower. It's just exponential.
There are examples of situations where people found, Goswami and Ali Sinop, Ali Kamal Sinop. There's a problem with the solve using sum of squares, but instead of paying n to the d, they pay 2 to the d.
Huh.
So, yeah, so that's a famous example. So I'll tell you about it.
Okay. Yeah, because I mean, the question is kind of what bases are you using, and that's kind of what we're going to see. Like, if you're using, the basis that we usually use for sums of squares is just a monomial basis. And that's good for certain examples, but it's not always good. It might not always be the smart choice. So kind of the point of this talk is, what is a smart choice when you have symmetry? Yeah.
I have a question about, so doesn't the notion of degree depends on your basis, actually? So if you pick a different basis, I mean, how do you define?
I don't think that it depends on the choice.
So how do you define the
So my
degree function, or?
So my degree for me will be the degree within the polynomial that I square.
But the degree is with respect to the standard basis. You look at the
No, the degree,
No.
it's a linear transformation. You can choose any basis you like.
No, it's an
The
open
power-
basis, right?
No, but the powers of x, or the power of the product of x, xi, it's a normal notion of degree.
I mean, I completely see your question, because there's a recent paper by Monaldo Mastroili, he comes up with bases with very high degree, but that are very compact. You just have a few elements in them, right? And so then you would say, oh, the degree is very high in here. But then, if you see his method as a hierarchy, so then the rounds for him, there's really very few rounds for certain problems, even though the degree is very high. But for me, degree still really means the degree of these polynomials. We still have something where we'll just keep, if you're not able to do it for degree 1, then you'll go for degree 2, degree 3. It's just that the basis that I'm going to be using.
I guess in our case, in the cube, you just choose the multilineal, the polynomial is your basis, monomial as basis, right? And then it's.
But see, that would be, if you do this, then
You
it's,
don't do that.
yeah, this will not be good.
Okay.
But that would be the natural thing that you would
Anna,
normally
just,
do.
you correct me if I'm wrong. The notion of degree, the smallest degree in which a sum of square proofs exists, is independent of the base.
So
Just independent of the base.
Yeah.
This is independent. We are not talking about runtime or anything. Just you can represent a polynomial in any basis you like. The degree will not change. And the degree of proof will not change.
That is true.
The runtime may
I
change.
agree, but-
Yeah, so it doesn't matter.
That is true, because any basis will be able to give you, your FI, right? So some linear combination of the elements of your basis will give you this FI.
She's trying to minimize something else, the runtime, dependence of the number of variables. The degree will be always the degree.
But using the degree as being what is behind the rounds of your hierarchy is not necessarily always the best idea, which I think is kind of what you were thinking about. And so there are examples of that. In our case, we were still using the degree as being the rounds, but we're going for another basis so that this here, this n disappears, because we don't like this n. Okay. So in the case when you have just Sn, the normal action, the direct action of Sn onto your ground set of elements, how to use symmetry for sums of squares was well understood in 2014 by Greg Beckerman, James João Gouveia, and James Pfeiffer. And they left the case greater or equal to 2 open. And so it might not be clear why we care about a case where you have the induced action. So let me give you 2 very straightforward examples, but there's many others.
All optimization problems on graphs are symmetric, right?
Yeah.
All this.
Yeah, and so the point is, this is for problems on vertices, this is for problems on edges, right? So for example, Turin type problems are good examples. So you're given a fixed graph H, and you want to know what is the maximum edge density of a graph on n vertices that doesn't contain H as a subgraph or as an induced subgraph, you choose. And in particular, since this is hard, you might already be happy to say something in the case when the number of vertices goes to infinity. So I'm maximizing the number of edges, really, in my graph. So that's a symmetric polynomial. And my variables are edge variables. So if this is on graphs, this will be the 2 subset discrete hypercube. If it's on k-uniform hypergraph, right, you can do this problem for k-uniform hypergraphs, then it will be my k subset discrete hypercube. So this is exactly your setting, right? I mean, I really love this problem. Does everybody know the history of this problem?
I'd be happy to hear more.
Okay, so Turan was a Hungarian mathematician, and he did this while he was in a labor camp in Transylvania. And so, you know, he was a mathematician, so not the strongest guy. And he had to carry railway ties, like the wood pieces that go between the tracks of a train. And he was doing it very badly. And so one of the other guys was just like, oh, Turan, you know, like, you really suck at this. And one of the guards overheard him. And he was like, Turan, like Paul Turan? And he was like, yeah. And the guard was just like, I know your papers, you're amazing, you should not be doing this. So it turned out that the guard was an engineer. And so you'd think, well, no, engineers do not read math papers. This is not true. This is not a credible story.
Hungary is a weird country.
It turned out he worked in a printing shop that printed scientific journals. And so he had seen Turan's name many times. So he assigned him to a much easier job. He assigned him to be basically at the entrance of the lumber yard and to just go, the lumber is there. And so all of a sudden he had way more time to think. And so at first he tried to think about this other problem, but he didn't have pen and paper, right? So he had to be able to do it in his head. And he had heard of Mantle's theorem, right? So Mantle's theorem is the smallest example of a Turan type problem. It's the case where you're forwarding triangles in a graph, right? So then the max edge density is 1/2 as the number of vertices goes to infinity. And he had heard about that, and he had heard about, you know, maybe trying to generalize that to forwarding cliques of size A. And that's when he worked on it. And I have a quote so he survived the war, right? Because he only had to point at lumber. And he wrote about this experience and thinking about this particular problem over there.
You can
And
see that those running advance is a relaxed audience.
what? I'm clearly not very good with technology.
It was World War II. Right?
Okay, I got it. I got the quote. Yeah, during World War II. So he said, then this formal extremal problem occurred to me, and I immediately felt that here was a problem appropriate to the circumstances. I cannot properly describe my feelings during the next few days. The pleasure of dealing with a quite unusual type of problem, the beauty of it, the gradual nearing of the solution, and finally the complete solution made these days really ecstatic. The feeling of some intellectual freedom and being, to a certain extent, spiritually free of oppression only added to this ecstasy. So I think it's a pretty nice problem, mathematically, but also historically. And it fits our setting. Great. Another problem that fits our setting is a Ramsey type problem. So you want to color the edges of a complete graph on n vertices either with ruby or sapphire, and you want to find the smallest number of vertices n for which you're guaranteed a ruby clique of size r or a sapphire clique of size s. So the most famous instance of this is the case when r and s are both 3, right? So there are 6 of you, so it's guaranteed that there are at least 3 of you who mutually know each other, or at least 3 of you who mutually don't know each other.
Not in this graph.
And so, right? With 5 people, it wouldn't work. You know, if I say that red is people don't know each other, blue they know each other, then oh yeah, here there are no 3 people who mutually know each other or mutually don't know each other. Whereas for 6, no matter how I would color it, yeah, I would find a monochromatic triangle. And so we know the case when R and S is 4, both 4. We don't know when they're both 5, right? We know it's between 42 and 49. Still don't know, which is kind of ridiculous. Elders famously said, you know, like if aliens came to Earth and said, you know, you need to solve this problem when R and S are both 5. You have a year. You know, then we should just put all the smartest people in the world in one room with the best computers, and we'd probably be fine. If they ask for R and S to both be 6, then we should spend that year preparing to retaliate and just really attack. But we didn't really have symmetry then, so you know, maybe now by using symmetry we might be able to say something better. And so this fits our setting exactly as well, because what are we optimizing here? So really here I'm trying, let's say in that case, I would want to say for 6 vertices, I have to have a monochromatic triangle, so that if I forbid monochromatic triangles, then I shouldn't get a solution. So I want to show unfeasibility. So I'm really going to try to show that -1 is greater or equal to 0. So that's how I'm going to show infeasibility. So -1, well, that is a symmetric polynomial. It is invariant under Sn. And I have edge variables. I could do this for K-uniform hypergraphs as well. So this fits our setting as well. But there's many other decision problems where you have variables that have many indices. So it's not just in graph theory, but I do mostly graph theory. So these are the examples I prefer. Okay, so let me make this example really crystal clear. Just to make things simpler, I'll stick to edges and not K-uniform hypergraphs, so just good old graphs. So my K-discrete subset hypercube will just be indexed by coordinates by pairs of elements of my ground set.
You should know that combinatorial is like to call it a slice of the hypercube. You don't use the word slice. Like this is a 2-slice, it's K-slice.
Okay. That's good to know. We're wondering how to call this hypercube.
Yeah, there's a lot of, yeah, so Yuval Filmos just gave a talk here, a long talk serving, you know, tools of association schemes, which are very relevant.
Yeah.
Okay.
All right, so let's look at the easiest example of all. Let's look at Mantle's theorem. So I'm forbidding triangles on a graph on n vertices. So how would I do that with sums of squares? Well, I would write the following program. So I'm going to have variables xij for every pair of vertices I and j. And I'm going to say that xij is 1 if I put an edge between I and j, and 0 if it's not. So my first set of variables ensures that every edge variable is either 0 or 1. I don't have any half edges. And then I need to make sure that I don't draw any triangles. So if I look at any 3 vertices, then 2 of them should not form an edge at least. So that means that the corresponding edge variable should be 0. So if I take the product of the 3 edge variables, I should get 0. So okay, I have a triangle-free graph on n vertices, and now I want to maximize the number of, edges. I want to maximize the edge density. So I count the total number of edges I drew, and I divide by the total number of edges there could have been, and choose 2. Okay, so if I want to get Mantle's theorem, I should show that this is at most 1/2 plus some level of error that goes away as n goes to infinity. Well, that's the same thing as showing that 1/2 plus that little error minus my edge density is greater or equal to 0. So I'm really trying to certify non-negativity. So I can always think of optimization as showing non-negativity and vice versa. So I want to show non-negativity whenever these polynomial equations hold, so I can do sums of squares modulo ideal. So I want to find some positive semi-definite matrix Q and some degree D, such that I can write this as a sum of squares modulo my ideal, where my vector V here will be a basis of the elements of degree at most D of my quotient ring. And so my ideal is generated by the polynomials from the previous slide. Okay. So, I mean, you've seen a few talks about sum of the squares before. You know that we see it as being this very, very strong technique, right? And that it's going to revolutionize. Well, maybe you don't believe it, but I think it's very strong, right? It has a lot of potential for proving and disproving many conjectures, and it has already done so for many examples. So here, for this old problem from 1907, I run into trouble. The runtime would be the number of variables, and choose 2, to the order of the degree that I need. I told you the degree represents how hard the problem is. So here, this is a problem, the proof is 1 line long from 1907. I imagine D will be very small. But even if D is very small, I want to do this for any number of vertices n. In particular, I want to do it as n goes to infinity. And then I'm telling you semi-definite programming, which is this very amazing method, cannot do Mantle's theorem from 1907. So what are we doing wrong?
You have to be careful when you are saying it in general audiences. Polynomial time is still considered pretty good.
It is considered very good. It is considered very good. But here, for this setting, it's not good enough.
Yeah, exactly.
Right.
You just want to improve it, to make it more efficient. That's good. Yeah.
No, polynomial
Making it constant time is better. Yes.
Polynomial time is often very, very, very good. And I mean, it is amazing that semi-definite programming can be sometimes used in polynomial time, right? I mean, it's a generalization of linear programming, which yes, can be done in polynomial time, but linear programming is so much weaker. So it's already quite amazing that polynomial time sometimes works when D is a constant. But
What is D in this case, actually?
what?
What is D in this case? Is it something like that?
So it depends if you cheat or not.
Depends how you do it.
It depends how. So we cheat a little bit. So we get D is 2. But so this is the kind of proof that I would want to get for Mantle's theorem. So this is actually a sum of squares proof. So I have a 2 by 2 PSD matrix. Oh, sorry, degree 1. Even better. Yes. So I have a 2 by 2 PSD matrix. I have a 1 by 1 PSD matrix. So really, I have a block diagonal PSD matrix that's 2 by 2 and 1 by 1. So really, a 3 by 3 PSD matrix. And so instead of taking a vector of all my monomials of degree n most d, which there would be infinitely many of, right? I take some smart polynomials that say something about symmetry, right? So this is, fully symmetric. This is not fully symmetric, but it retains some information about symmetry. And I'm going to give you an idea very soon about what kind of symmetry I'm retaining here. And so that's what we want to do in general, and that's what we will be able to do. So I want to find some sums of square certificates that exploit symmetry, that have constant size, so 3 by 3 in this case in total. And the entries are functions of n. So this is going to be a certificate for every n, and in particular is going to be a certificate as n goes to infinity. Okay, so how will we get that? Well, we need a little bit of representation theory. Anybody afraid of representation theory?
Not after you give this case, nobody will be.
Okay, so nobody has any qualms? Anybody knows representation theory? Can I skip this? No? Okay. So I have my quotient ring, right? And I'm keeping the elements of degree n most d. So this is from the vector space from which I will build my squares, right? And so this is some big vector space. And so what representation theory tells us, really the only thing that we care about, is that you can take your big vector space and break it down into a direct sum of smaller vector spaces that give you some information about symmetry. Okay, so in this case, because my vectors, I have the symmetric group acting on my vector space, I really have an Sn module. And so because it's a symmetric group, what representation theory tells me is that I can decompose my big vector space into a direct sum of smaller vector spaces that are indexed by partitions. So this is called the isotopic decomposition, and each isotopic is indexed by a partition of n. Partition being a sequence of positive numbers that is non-increasing and that add up to n. So 5, 3, 3, 1 is a partition of 12. And so then, usually if you know some representation theory, you would say, okay, well, after my isotopic decomposition, I can still decompose each isotopic even more into smaller vector spaces by using irreducibles. And that's not what we're doing. We're doing something that's kind of like orthogonal to it. So we are decomposing each isotopic into a direct sum of W tau lambdas. So what are these guys? So for each partition lambda, I have a shape. So for the partition 5331, I have a shape where the first row has 5 cells, 3 cells, 3 cells, 1 cell.
Lambda at this point is just names for
A partition.
subspaces.
Yeah.
Yeah, they are partitions, but they index the irreducible representations of the symmetrical. So it's just a name for
Yeah.
those who didn't see it yet.
Yeah. And so then a standard tableau of shape lambda is just going to be a filling of these cells with the numbers from 1 through n in different cells. And I'll say that a tableau is standard if when I read from left to right and from top to bottom, I'm always increasing. So for any tableau, I can think about the row group. So these are any action of Sn that fixes the rows of my tableau, that send any label in my tableau to the same row that it started in. So for example, the permutation 1, 6 is part of my row group for this tableau, whereas the permutation 1, 12 is not, because then 12 and 1 would not end up on the same row that they started in. And so I'll let W tau lambda, so these guys, to just be the subspace of points of my isotypic that are fixed by my row group. So my W tau lambda are going to be invariant under my row group. And this is the part of the symmetry that it's going to retain. And just some definitions. N lambda, I'll let n lambda be the number of standard tableau of shape lambda. And m lambda will be the dimension of W tau lambda. If you know representation theory better, that's also the multiplicity of your irreducible. So I had my big vector space, right? So the place where I'm building my squares from in my sum of squares. And so I'm saying it's going to be a direct sum of W tau lambda for all standard tableau of shape lambda for all partitions lambda of n. So the whole dimension is going to be the sum of the m lambda times n lambda, since I have n lambda standard tableau and each of these guys have dimension m lambda. Okay, so we're not the first people who have thought about using symmetry for sums of squares. And so the groundbreaking work was done by Karen Gatterman and Pablo Parrillo in 2004. So what was their idea? They said, okay, how do we do sums of squares modular ideal? We say that P is a sum of squares of degree D modular my ideal if and only if there exists a positive semi-definite matrix Q such that P is equal to V transpose QV plus some H that is in my ideal, right? Some H that I know is 0 for every point that I care about, where V is a vector of basis elements of the elements of degree at most D of my quotient ring. So here I could have taken any basis, right? Including the, just all monomials of degree at most D, and then, multilinear ones if I'm over the hypercube, and maybe I can solve some other ones if I have other constraints and whatnot. So their idea was to say, don't just take any basis. Take a basis that says something about symmetry. Representation theory tells us that, oh, this happens, right? We have this nice decomposition of my big vector space into smaller vector spaces where this tells you something about symmetry. Do this. Find a basis for each W tau lambda, and so then you'll get a basis for V. Use such a basis. And so then when you do that, what happens is that this big Q over there, which you know nothing about, becomes very structured. So you're going to get one block for each isotopic component, so for each partition. And then within each block, you're going to get one block for each standard tableau. And each of these small blocks within one big block will be exactly the same. So you know tons of zeros, and really since all of these small red blocks are all the same, you just need to keep one. You just need to keep one of the blue blocks and so on. So that means that in total, instead of having something of the size of the sum of the m lambda n lambda, well, since you just need to take one of the n lambda standard tableaus for each partition, you really just have an SDP of the size, the sum of the m lambdas. So it makes the size way smaller, and also tons of zeros. Okay. So that was great work. It helps a lot. Still not good enough, right? And it's just like saying, polynomial time is not good. Here, like this was amazing work, but for us, it's still not good enough.
You're just reducing the multiplicities to 1.
Yeah.
Yeah, that's the only thing you're doing.
Yeah. And so, what's the problem? Well, how much smaller is this? Well, m lambda, it's actually really hard to calculate what m lambda is. And in most cases, m lambda does depend on n. And certainly the number of partitions of n depends on n. So the size still depends on n, which is what we're trying to avoid. The other thing is, you need to find a basis for each of these w tau lambda. That's not easy. So there's an algorithm to find such a basis, which we call a symmetry adapted basis, but the complexity of it depends on n. So those are the two problems that we decided to try to resolve. So
this is not for the slice. This can be used for anything.
Oh yeah, this method from Gataman and Pahilo can be used for any group. You don't have to have a modular ideal either. It doesn't have to be over the hypercube. So this is a very, very general method. You can really do this for any group without a problem, and not over the hypercube.
We still didn't define what symmetry adapted basis is, right?
No,
So it's just a basis for each of these w tau lambda.
Any basis?
Well, they use a particular one to make it even nicer. So it's going to be an orthonormal basis of each of these guys.
Just an orthonormal basis for each guy, and then you compose all of them together to a Buick basis, and that's your symmetry adapted.
Yeah.
So the symmetry adaptivity just means that
That you're following this decomposition. Yeah. Yeah. But yeah, it's actually really hard to create, and it's not intuitive at all. So what did we show? We said, okay, do this method of Gataman and Pahilo, but don't do it for all of these blocks. Just keep a few blocks, the first few blocks, and we tell you exactly which to keep. The number of blocks that we tell you to keep is independent of n, and the size of the m lambda for each of these blocks is also independent of n. So then you get a size that is independent of n. So you just need to keep things before a certain hook. So for
particular problems, not for every problem.
We're in the k-subset discrete hypercube. So for every problem for the k-subset discrete hypercube, you just need to keep partitions that are lexicographically greater or equal to n minus kd 1 to the d. So that's a big hook where, so k again, we're in the k-subset discrete hypercube, so if we have a graph problem, this would be 2. And so the number of such partitions is independent of n. And for each of these partitions, m lambda is also independent of n. And this is way overkill. This is way more than we need, but certainly whenever you're over the hypercube, this will be sufficient. So in the case of the Mantle proof, I just needed to keep n and n minus 1, 1. So this is the sum of squares, like the block that comes from this partition, and this is the block coming from this partition.
It means that the ideal that will be 0 on all the other, will be 0 on all the other partitions, on all the other vectors.
Yeah, you don't.
You have no projection in the.
You don't get anything more by using the other partitions. Okay, so that's good. So the size now of my program is independent of n, provided that d is independent of n. But I still need this symmetry adapted basis. So there, a very naive idea works. So instead of a basis, use a spanning set. So for each of these w tau lambdas, use a spanning set only for the partitions that we need to keep. And of course, well, your spanning set is going to be bigger than a basis, so you don't want to suddenly get dependence on n again. So you need to make sure that these spanning sets have size independent of n, and you want them to be easy to generate. You don't want to have some algorithm that's going to have a runtime that depends on n. And so they do exist. And so here are two very easy ones. So I can take the my monomials and symmetrize them under my row group. That works. And then I get another one for free by just taking an appropriate Möbius transformation of these. They span the same thing.
What is the second one? Is it separate basis?
It's
First is the basis.
so this is not a basis. This is a spanning set. And now I just take the Möbius transformation of these guys.
You add them, or the first is a spanning set.
This is already a spanning set.
Oh, okay, so you can find another one.
By just transforming this one a little bit, that has the same spanning set. So this is good. So this means that whenever you're trying to certify non-negativity of a symmetric polynomial over the k-subset discrete hypercube, your runtime will depend on D. D can depend on N, but okay, your dependence is really on D. So this is the first good news. The second good news is that this very much relates to the work of flag algebras by Sasha Hasbahov. So let me.
Are you going to prove this statement that these are the only representations you need to take?
It's actually very easy. I wasn't going to do it. We can talk about it later on. But so basically think about a monomial of degree D. So how many vertices can be involved in a monomial of degree D? At most k to the D. And so then if you have this hook where you have kd vertices here, then you can put your monomial in here, basically. So, if you have the monomial, I don't know, x12, x35, x27, then I could put 1, 2, 3, 5, 7 here, and everything else here, so 4, 6, 8, and so n goes to infinity, or n can be anything, it doesn't matter. And so this is going to be invariant under the row group of this tableau, right? So and my w tau lambda is going to already, I do need a little bit of representation to know, theory to note that this is included in the direct sum of the partitions that are greater or equal to lambda, so of my isotopics. So then I'm good. So
there must be a simpler way to see it. I mean, it's not clear that isn't there a direct, just bypassing?
It's not what?
Bypassing the representation theory completely. I mean, you are saying, what you are using is that monomials are at most of degree D. You have the action of the symmetric group, and you want to say that. So you will just symmetrize all polynomials of degree 1, 2, 3 up to D.
Mm-hmm.
Why under the symmetric, under the acting group? Why is it not obvious that this is enough as a base of a polynomial?
Oh, like under the full symmetry group?
No, the full symmetric group on the no, just on. There are a finite number of subgraphs of degree D.
Yeah.
That's
Yeah.
right. There's some number of degree, non-isomorphic graphs of degree D. Symmetrize each of them.
Yeah, and that's exactly.
So why do you need representation theory? You can just say that the proof must necessarily, because of the symmetry of the action on your optimization function, the solution must be symmetric. If it's symmetric, then it will be spanned by these polynomials, isn't it? Why do you need to go into all these?
I don't see it the way you're doing it, but so I kind of see. I can see. What?
Is it true?
Is it true?
Yeah, what I said. Yeah,
well, more or less.
This will always be. So
it is.
I'll repeat what I said.
It is true. It is true because what you're basically saying is what Sasha did.
Yeah,
and so this is the relationship between what Sasha did and we did.
Nobody knew any representation theory. All they knew is graph theory.
Yeah.
Right? Graph theory, questions about, you are asking about questions about graphs, which are independent of the labeling of the vertices, like the number of subgraphs of a certain type.
Yeah.
Right? And you want a sum of square proofs for whatever.
But
So
see,
suppose if you get one sum of square proofs, maybe not symmetric, you can symmetrize it and it will still work. Right? That's
yeah, that's true.
So symmetrize it. When you symmetrize it, you see that what you get is a sum of polynomials which are symmetric and of degree d. So what are they? What can they be? Well, every subgraph, every non-isomorphic subgraph like the one you wrote, provides one such polynomial. So all you need is the polynomials which are the symmetry of presence of a particular subgraph of size, number of edges at most.
But so you're assuming that there is a sum of squares proof to start with, right?
I'm assuming. We are assuming there is a sum of squares proof. Why not? And then we are concluding that there is a symmetric sum of squares proof, which is independent of size.
For sure. But so, what degree will you need? So this is kind of one of the nice things about our relationship to Sasha is that, like if you work just directly with graphs, it was unclear, how strong was flag algebras? What could it do? What could it not do?
Flag algebras, I care at this point only about Mantle's theorem.
Okay.
Mantle's theorem was proved. In fact, one can easily find a degree 3 proof of Mantle's theorem. Maybe not symmetric. I mean, one can see that there is.
Oh, but once you have if you have a degree D proof of anything, then by symmetrization, you know that you will need also at most degree D here, right? You're fine.
So maybe I'm missing something. There are two parts to this. One is that you get independence of n, but before that, it's just that the degree is low. Do you need representation theory to prove that the degree is low? I don't think you did.
No, so we have no idea what degree we need for anything, right? So the degree depends on the problem that you have.
It does, yeah.
Right.
So for any, that's right. But for any degree, you will need only the number. Oh, this is even smaller. I'm just trying to understand. If the degree is d, then you will need just.
So we're saying.
So why isn't this for you? D was something in Mantle's theorem. It's 3.
Yeah. So here we're also assuming there is a sum of squares proof, right, of degree d.
Yeah.
Right, and so usually to get it, you would need a PSD matrix whose size also depends on d and on n. And so we're saying the PSD matrix that you need to get only depends on d, not on n.
Yes, but doesn't it follow from the existence of a proof of
But,
degree?
but how would you search for it?
Yeah, I'm not, at this point I'm not searching. I'm just trying to understand what you're claiming. The degree of the proof is d. Some d, I don't know, whatever it is.
Yeah.
And I'm not talking about the runtime and the size of the positive definite matrix. I'm just talking about the degree. So there is a proof of degree d for some d. Somebody found it, I don't know, or it exists. We take it, we symmetrize it under the action of the group. Now we have another proof. This proof is symmetric. When we can look at the polynomials used in this proof. Because we symmetrize, it seems to me that a basis for the proof, a basis we can use in another proof, will be just polynomials which are the symmetric copies of any particular graph of degree at most.
Yeah.
Is it true?
Yeah.
Yeah, so I didn't use any representation theory in this argument.
Yeah. Yeah, you didn't.
So we can check it later. I just want to clarify that.
Yeah, it's not very hard. I mean, I think we're
No, it may not be hard, but you see lambdas here and w lambda, and it's not clear.
So I agree. But so how would you generate these bases? And so this is what this is
talking about the
doing.
existence of a proof whose size is independent of n.
Yeah.
Okay.
Yeah. That should do it. Okay. Any more questions?
What's K?
So K is you're in a K subset discrete hypercube.
okay.
So for us it's 2 most of the time if you're thinking about a graph. Otherwise, K uniform hypergraph. Yeah.
And so like your dependence ends up being like the number of partitions of k times d or something.
And the number of monomials. So, but all of these is independent of n. Yeah. So how does this relate to flag algebras? So what is a flag? So a flag is just a partially labeled graph. And so what Hasbahov does with these partially labeled graphs is to certify a symmetric inequality that gives a good upper bound for turn-type problems and other types of problems too, but just, let's stick to our setting, so for turn-type problems. So they might not be the flags that you've seen before, right? There's many flags in math. Why have another kind of flag? Well, because Sasha thinks that they're the best named flags. Basically, what you do is that you send these small labeled graphs into a bigger graph. And these vertices that are labeled are going to be sent to a particular place. So you know exactly where vertex 1 goes inside your bigger graph and where vertex 2 goes. Everything else can go anywhere. So you have a part that goes to a fixed place, and then the rest can go anywhere. So it looks like a flag. This is why he called them flags. And that's why we needed yet another thing called a flag. So the key features of what Sasha does is that you have sums of squares of graph densities, right? So you don't have sums of squares of polynomials. You have sums of squares of these densities of these flags inside other graphs. And a very, very nice property is that n disappears. So it doesn't matter, well, you're setting this into a graph where the number of vertices n goes to infinity. So this n going to infinity business is not problematic. In another way, though, it's kind of annoying because you can only do it for n going to infinity, right? You're doing only infinite graphs, so you're only getting asymptotic results. And you get also this error of order 1 over n because of where you send these vertices. You're kind of assuming that they're going to different places if they could actually go to the same place. So you have this error of order 1 over n, which means that if you're doing some problem where the optimal solution gets eaten by this error, then you cannot say anything. But overall, it's a very strong technique, and so Sasha was able to prove some really amazing things with it. So for instance, for the turn-type problems, if you're looking at the 3 uniform case, so every edge is made out of 3 vertices, and you're forbidding cliques of size 4, then the maximum edge density as the number of vertices goes to infinity is believed to be 5/9. And so Tuhan conjectured that, and he came up with an example that actually yielded 5/9. And now we know continuously many examples that give 5/9, but it still hasn't been proven. And so the best bound was given by Hasbahov, a bound of 0.561666 using flag algebras. And then he said also, well, if you forbid a second graph instead of just the cliques of size 4, if you forbid a graph on 4 vertices that induces exactly 1 3-edge, then the max edge density is actually equal to 5/9.
Sorry, what is edge 1?
4 vertices that induce exactly 1 edge. Yeah. So flag algebras are pretty cool for this. And so
Many people have seen.
a little bit.
So this part of this is Rasborg's take on the part of extremal combinatorics, trying to do extremal combinatorics in the limit. So they have building an analytic theory for graph theory. And this was done before by Lovas and Segedin in a very different way. These are the graph limits thing. In both cases, it's you want to work on infinite objects. That's why n doesn't exist.
Yeah. So Abby at Oberwolfa in 2015 asked Sasha, is there a link, right, between sums of squares theory and flag algebras? Because there's these sums of squares of graph densities, right? So it's a very natural question to ask. And Sasha, for the first time ever, was wrong and said, no. And
This is the first time I know. The only time I know he was wrong.
mathematically at least. So what is the connection between sum of the squares and flag algebras? So basically I told you that for us, our spanning sets would be symmetrization of monomials under row groups of tableaus. So let's say that I give you a tableau. Really, I only need to keep hooks. So I'll transform this into a hook by keeping my first part to be the same and then putting everything else in the tail. So if I symmetrize the monomial x12, x13, x14 under this hook, well, really this is kind of like just S4, right, on 2, 5, 6, 7. So I'll get x12, x13, x14, and then 2 can go to 5, or to 6, or to 7. Everything else is fixed. I could have thought about this as a density of a flag within a graph. And so the only difference is that here, you can do this on any graph. And so now I can think, okay, what is the density of this particular flag inside any graph? And so let's just see for a particular graph that we do get the same thing. So I want to send, and so there's this concept of where do I send my fixed vertices. So let's say that I send vertex 1 to 1, vertex 2 to 4, and vertex 3 to 3. And so let's say that this is my big target graph. So I send 1 to 1, 2 to 4, so blue to blue, and green to green. And now I want to know, well, where can I send my last vertex so that I get this graph, this subgraph? So here, I get 0 because there's no edge between my red vertex and my blue vertex. So no matter where I send my last vertex to 2, 5, 6, or 7, I will not get this subgraph. If I add this, and so I would have gotten exactly this if I evaluated my polynomial on this graph, right? So the variable x14 is 0, so I get 0 plus 0 plus 0 plus 0. I also get 0. If I add the edge 14, then okay, I can send, so I have an edge between red and blue and red and green, and I want to have an edge between red and the other vertex. So I can send it to 2, to 5, to 6, but not to 7 because there's no edge there. So 3 out of 4 places where I can send my last vertex gives me the subgraph. If I had evaluated this polynomial on this graph, I would get exactly the same thing. So I would get a 1 here, a 1 here, a 1 here, and a 0 here because x17 is 0. But all my other edge variables are 1. And so same thing if I remove 3, 4 here, not a problem, there's no edge there, so I still get 3/4 and also there.
You consider every graph counting problem is a polynomial.
Yeah, exactly.
Evaluation on the graph.
And so the relationship comes with, so this is kind of the Lovász way of counting. If I want the Hausbach way of counting, I need to look at the Möbius transformation. And so when I do that, I get the induced subgraph. So here, I want to know, okay, in how many ways can I send my last vertex to get an induced copy of this flag? And so here there's 0 ways. And also here, because I have an edge between the green and the blue vertices, and here I don't. So in the induced case, I want non-edges to also be non-edges. Whereas in the previous case, I only cared for edges to be edges. So in this case here, this is the only case where I don't get 0. So I cannot send this to 2 because then I have an edge between my black vertex and my green vertex, which is not supposed to be there. I cannot send it to 5 because then I have an edge between my blue and black vertex, which shouldn't happen. I can send it to 6, right? So 6, 1, 3, and 4 is actually an induced subgraph of this where those vertices are sent to the correct place. And I cannot send it to 7 because then I don't have an edge here. So 1/4. And these are exactly the flag densities that Hausbach uses. Exactly. So what this is saying is that the flags provide actually spanning sets for my row group invariant subspaces of my isotypics. And so, yeah, they're just, you know, little graphs of a fixed size. And so we tell you exactly on how many vertices that you'll need to keep. And so they have a size independent of n. And so that means that if you have a polynomial that is symmetric and that is a sum of squares of degree d, then its non-negativity can be established through flags on KD vertices. Even in restricted cases when you're saying things about the type of your graphs in Hasburov's theory. So for the proof of Mantle's theorem, what this is saying is that, well, I had that the degree that I needed was 1 in our proof. So that means that since k is 2 here, because we're on the edge case, not hypergraph, then I need at most 2 vertices, and these are all the flags on 2 vertices. That's all I could potentially need. And so the year before, we had shown that every flag sum of squares polynomial of degree kd can be written as a succinct DSOS. So that means that really flag methods are equivalent to standard symmetry reduction methods for finding sums of squares certificates over discrete hypercubes.
And in all his calculations in the proofs of some of his theorems, when he ran his semi-definite programming, he was already using this symmetry, searching for inequalities between graph densities.
Yeah, so
he was already implicitly using such a basis.
I've asked him many times, how does he choose, which flags to use, right?
I'm not even asking which flags to use, but suppose he was doing in Mantle all the flags that you listed, the basis for the he would run these big semi-definite programs in order to get the inequalities.
Yeah.
What basis was he using? Wasn't he using the same flag basis?
No, that's the thing. So how his computer program wouldn't go through basis, right? He would just go through different graphs, which he had no real idea what would work. So it was just by having a computer program just trying many, many different possible things. It's not a systematic method.
But he was running semi-different programming, right?
Yeah.
Yeah. So what was the?
But so he would just try many different.
Monomial basis.
Yeah. Well, not monomial basis, but just sets of flags.
Okay. I didn't know.
Yeah, and I've asked him many times. So how do you choose these flags to use, right? And so he just has a program that just really runs through a bunch of them and hopes that one of them gives something good.
Yeah, but you would still symmetrize the flags, right? I mean, symmetrize the 3 vertices in the flag. Why wouldn't you? They can go anywhere, right? Like you did in this example, 2 could go anywhere, right?
Oh, sure. I mean, that's actually exactly what his flags are. So this is exactly what he would use. He would use this 0 or this 1/4, or these are the numbers he would use. So he does symmetrize in that way. But should he use this flag or some other one? And so that's kind of one of the nice things, is that these methods are equivalent. And so in the sense that if you have a proof of flags, then on KD vertices, then we can have a D sum of squares proof, and if we have a D sum of squares and vice versa, we can get a flag proof. But yeah, for the flags, how to search through these proofs, how to decide which flags to use is not an obvious thing. And so Sasha has great intuition, and sometimes he uses intuition to help him, but in general he doesn't know which ones to use, and it's really just a computer program. Whereas for sums of squares, you just increase the degree. And so then maybe it's overkill in a certain way, but then you're being very systematic. So if you don't have a good idea about what will work, using sums of squares can make sense. Okay, I'm already way over time. Just 3 very nice consequences. With flags, you don't have to have that n goes to infinity because of the sums of squares, right? So normally for flags you would just have n going to infinity, but now when you see them as polynomials, you can have a fixed n. So you could do Ramsey numbers. Before, when you wanted to use flags for some problem where n was fixed, you needed to come up with some very clever way of turning it into an infinite problem that's equivalent, right? So for Ramsey, yeah, some people found out, oh, you can blow up things in this way, and then you get something that's equivalent where you can use flags. But for every problem, you have to have a great idea about how to transform it. Whereas here, just use the polynomial equivalent and you're fine. Another nice thing is that I told you, like there's this error of order 1 over n that comes with flags. So that means that for a certain problem, you're eating up the optimal solution with it, so you cannot say anything interesting. Whereas if you use polynomials, you get to decide exactly how precise you want to be. Do you want to be exact? Do you want to have an error of order 1 over n so that your degree can be a bit less, or an error of order 1 over n to the 5? I don't know. Whatever you want, you can decide. And so you can be as refined or coarse as you want and still use flags when you use them as polynomials. And then
which work of Verassos it is?
what?
Which work of
It's if you forbid cycles of length 4 in a graph and you want to know what is the max edge density, then
or you want exactly the error?
yeah, the error there would usually, because it's sparse, the error would eat up the 1 over n. Then another nice consequence is that in sums of squares theory, we do know of many examples where the degree depends on n, right? So where sums of squares fails. And it was kind of a question about, when do flag algebras fail? Can they do everything? I mean, for a while, Sasha would always say, flag algebras can do everything. What does that mean? So, I mean, we've known for a while from the work of Hamed Hatami and Sergei Narin that, well, actually non-negativity of graph density inequalities in general is undecidable, but there were no real good example. But so if you use the Grigoriev example, then you get a very nice simple example that cannot be certified exactly with flags, but only up to an error of 1 over n squared. And Hasbro allows an error of size 1 over n. So that was actually my first open.
What is this? This is a knapsack example?
No, well, kind of. You could kind of see it as a knapsack example. It's the famous Grigoriev example that if you add up, half of the edges, all of the edges in a graph, and you remove about half, and you multiply that again with itself, but just one less, then this is clearly always non-negative, right? So either, the number.
So this has nothing to do with graphs. It's just you have n variables. Yeah. So it is a knapsack.
Yeah, you can see it as a knapsack.
Just a knapsack example. You want to say that the sum of Boolean values cannot be fractional.
Yeah.
Right. So that has a linear degree. So it has nothing to do with graphs.
Yeah, it has nothing to do with graphs, but you can put it in a graph setting. So and then exactly, and then flags cannot do this well. Not exactly.
Cannot do this well with one.
Because the sum of squares here has to have degree at least a big degree, and so since we have this equivalence between flags and sums of squares, you know that you'll need the number of flags that you'll need will go to infinity if you want to prove this exactly. But there's this error of 1 over n. So this was my first open question, is to find actually a family where even with this error, you'll still need infinitely many flags. And so a few weeks ago, I was talking with Aaron Potoshin, and he seems to have an example of that now, using your technique. And I'll tell you more about the example in a sec. And another problem is just to provide certificates for open problems, right, using symmetric sums of squares. And so both of these things are things that are related, for me, to this problem. So this is something that Sasha proved. Here you have edge density, here you have triangle density, and you want to know where can graphs live. So you cannot have a graph where you have, all possible triangles and no edges, right? And so Mantle's theorem is right here. So if I have 0 triangles, then the maximum edge density is at most 1/2. If I have more than 1/2, then I have to have some triangles. And so this curve is pretty easy to prove. These are much harder. And so with flags, Hasbro proved that. But now he used the calculus part of flags, and so Aaron now has shown that if you fix an edge density here and you want to see, okay, that the max triangle density is here or here or here, then the degree that you need for the different parts keeps going up. And so that means that the number of flags that you need also goes up. So you won't be able to do it with a finite number of flags. But so such pictures this is one of the rare pictures that we know. So we know when you have an edge and a clique, how to do that. We know how to, if you have any two subgraphs on 3 vertices, but otherwise we really don't have pictures yet. And we don't also understand any picture in more dimensions, right? And so this is one open problem that we are working on to understand. So they're called graph profiles in different cases. And I'll stop here. Thank you. I started an Instagram feed, which, you know, looking in the room, maybe not everybody uses Instagram here. You're not my
Came yesterday to the party, there were all these babies. They all had Instagram.
But so it's I interview women and other minorities in math and computer science, and so every day there's some new interesting math or computer science or some of their experiences that are there. So if you were willing to be interviewed, I would be happy to interview you while I'm here. But yeah, you can tell your students about it if you have students somewhere. And I'll stop here. Thank you.